So hi all, welcome to this lecture 4 of Unconstrained Optimization. Uh, um, so the name of today's lecture is uh, Optimization in one variable, and we'll discuss optimality conditions. Basically conditions, basically what are the necessary and sufficient conditions uh, for a mm, for a point to be a local minima in one dimension. So what does that mean? We'll mathematically formulate it later, but first recall what we did in last few lectures. So in last lecture we defined various types of sets, for example open set, closed set, what are those, and bounded set, what are bounded sets, and based on that we finally defined what are compact sets, which are of importance for us, which mean that all the sets which are closed and bounded are compact set. So if I uh, tell you about it in R square space, so uh, every set that contains all the points and the boundary points, and it is bounded, that it can be contained in a norm ball, then it is compact and bounded. So it is closed and bounded, and hence it is compact. We also discussed what are continuous functions. We defined it. We also defined what are continuously differentiable functions. So basically all those functions whose first derivative exists and is continuous is called continuously differentiable function. And we basically represent them by C1. So basically this number on the top tells us how many, so let's say all the sets which belong to C1 will have their first derivative as continuous. And so let's say C2 means second derivative exists and it is continuous. And C0 by that definition means all the functions which are continuous. So these terminologies we'll use in today's lecture, so it's better to state them here. Then we also defined in last lecture what is a global minima, and we also defined what is a local minima. And what is the difference between these two? We said that, and it's so local minima is a point x star which for which fx star is smaller than fx, smaller than equal to fx, for all x uh, belongs to neighborhood of x star, some neighborhood of x star. So neighborhood means some delta x star plus delta x star minus delta. So if x belongs to this, and for all x belonging to this set, if x star is the smallest, then it is a local minimum. uh, and then there was something called a strict local minima, in which we remove this equality sign. So and why is it useful, we discussed an example as well. So so then we discuss Weierstrass theorem. So what this theorem says, that uh, that let's say we have a compact, and we have a compact set uh, for a function, and a function is continuous, then its maxima and minima will exist in that set. So any function whose domain is a compact set and is continuous in that set will have a maxima and minima in that set. That's what Weierstrass theorem said. So actually it's very intuitively clear. So this is where we ended the last lecture. Now in today's agenda, uh, in today's agenda, we will try to look at optimization problems in one variable. So today today's lecture, we'll deal with this problem, and this you will have we would have done mostly in your class 11th and 12th. So basically there was a chapter in maths called maxima and minima, in which you try to find a derivative, double derivative, and try to find the maxima and minima of those functions. So we'll do all those theories, but we'll also see why the derivatives caused it to be minima. We'll try to prove it, and we'll also go a step further to derive the optimality conditions, sufficient optimality condition, which will be enough for any continuous functions to for us to say that this local minima is a local, this minima is a local minima for a continuous function. That's what we'll do. So till now we have looked at constrained optimization problem. So let's say X is a subset of some n-dimensional real number set, and F is a function from R to R. So it's a real valued function. So its output is a single real number, but it takes n values from, like, because X is an n-dimensional set, n-dimensional vector space. Now we saw, so if we try to solve this kind of problem, minimum over x of fx, such that uh, x belongs to this capital set, then this is a constrained optimization problem. Why constrained? Because our input variable is constrained to be in a set x, and it cannot take all the real values. Then if as a special case of this constrained optimization problem is unconstrained optimization problem, in which R belongs to Rn. So it can take all real numbers. So this is called unconstrained optimization problem. Okay. Now this is our focus of this lecture series. But in today's lecture, what we'll want to look at is F from R to R, such that the input set is also a single dimensional real number, and it's unconstrained optimization. Basically, minimum over x fx such that x belongs to R. So this is what we want to look at in today's lecture. So moving ahead, so first question that we want to ask ourselves is, what are some necessary and sufficient conditions for a local minima? Okay. So for those who are why are we talking only about local minima? We discussed earlier that it is very difficult to differentiate between local and global minima, and there are a huge class of problem in which finding local minima does the job. So we'll try to focus on how to find local minima. Finding global minima is an extremely difficult task, which we're not looking here. So our aim is to find local minima of a function. So basically, what are necessary conditions? So necessary conditions are satisfied by every local minima. And sufficient conditions are, if these conditions are true, these guarantee local minima. Okay, so and if some condition is both necessary and sufficient, then that is equivalent to, like, that is if and only if minima. So basically, necessary condition will be like some condition C necessary, so local minima. If there is a local minima, it will imply these necessary conditions. If sufficient conditions are true, then we can say local minima. So they guarantee local minima. this is for sufficient, and this is for necessary. And if some conditions are both, then we are looking for such condition. Like if we can find these condition, we'll be sure that this is 100% local minima, and all the local minima also follow these conditions. So this is an if and only if condition. So it turns out that it is very difficult to find a local minima if the function f is not smooth. Let's say it's not continuously differentiable to some level, then it is difficult. So let's say a function is discontinuous, then it's very difficult to analytically find a minima. But local minima of are sufficiently smooth. Sufficiently smooth means it's continuously differentiable, or higher order derivatives are also continuous. Then should f is easy to find compared to non-continuously differentiable or non-continuous functions. So we'll discuss the first condition. So first, this is called first order necessary condition. So actually all these conditions you already know. So this condition you already know. I'll just state it first and then I'll discuss. So let f be uh, a set from R to R, a real valued function, uh, and f belongs to C1, basically continuously differentiable functions. Basically, first order derivative is continuous. That's what it's mean. Then, if we consider a optimization problem, minimum over fx, and x belongs to R, unconstrained optimization, then write it in red. If x star is local minimum of f, then f dash x star equals 0. So this is the condition that if some point x star is a local minima, then its first derivative at that point should be 0. This is a condition that you already know from your class 11th and 12th. That is that. Um, but can we prove it? Like, why is this true? Why is this true? So how do we go about proving it? So if you look at the statement, there are two statements. So if x star is a local minimum f, then fx star is equal to 0. So basically the statement is of the form A implies B. Basically it's saying that if A is x star is a local minimum f and B is f dash x star is equal to 0, then this is the statement. So A is x star is a local minima of f, and B is f dash x star equal to 0. So one very good method of proving such kind of statement is we assume not of B and then we prove not of A. So if we do this, we'll prove A implies B. So we'll do the same. We'll assume that let's say x star is a local minima, and and fx star is equal to, it's not equal to 0. So we'll do that. So let x star be a local minima of fx and f dash x star not equal to 0. So before moving forward, we'll also assume that let f is a continuously differentiable function. So because we are given that here, continuously differentiable, which means first derivative is continuous. I hope this makes sense. So yeah, we'll use this property here. So let's say we assume this. Now, if it is not equal to 0, let's assume f dash x star is greater than 0. So let's say this is the first possibility. And now let's assume a neighborhood around x star. So let's say this is x star, and this is x star minus delta. This is x star plus delta. So let's assume a neighborhood around x star. Let is equal to x star minus delta comma x star plus delta. Okay, let's assume this such that f dash x is greater than 0 for all x belongs to D. What does this mean? So we are assuming a neighborhood in which f dash x is greater than 0. Same sign as this. How can we choose such a neighborhood? So how do we know such a neighborhood exists around x star? Because we assume that f dash x is continuous. So let's say f dash x is positive here at x star. Then around it also we can always find a neighborhood where it will be positive because it is continuous. It just abruptly does not change this value. So we can always find a neighborhood around delta. Delta can be very small. That such a region has uh, f dash x greater than 0. So so we assume a neighborhood D where first derivative is greater than 0 around x star. Now we'll use truncated Taylor series, first order of problem. Okay. So what is the truncated Taylor series? First order. So for those of you who don't know, you can go back and look at the lectures on mathematical background too. There you can find it. So what it mean is any function f can be around x star, some point x star can be represented like this. So notice that this is not a approximate representation. This is exact representation, and where x bar belongs to x star comma x. So what does this mean? Let's say there is a function f. So it can be approximated linearly like this, uh, about around x star. This is not approximation. So this is an exact value. So let's say I know value of fx at x star. I want to know value of fx at x. So there exists a point uh, uh, x bar between them, such that this is true. This statement is true. This is what truncated Taylor series means. So with this, we'll go ahead and prove our statement. So let's assume x belongs to x star minus delta comma x star. So let's say it belongs to the left half of the plane D. Now let's analyze what the value of fx is. So fx is fx star plus delta f. Uh, so you can see if x is less than x star, x bar will also be less than x star. It implies x is less than x star, and x bar, because it is between x star and x, it is also less than x star. So delta fx bar x minus x star. So what is the sign of this? Because we are in neighborhood D f dash gradient, or sorry, here, because we are in single variable region, so we can, gradient is same as differentiation. So sorry about that. So it's same, it doesn't make any difference, but in single variable it's a first derivative. So this is positive because x is inside D. So this is a subset of D, if you can see. And we saw above in 1 that if x is in D, then f dash x is greater than 0. So this is positive. What about x minus x star? So x minus x star is negative. You can see from here. Because x is less than x star. So this whole quantity is negative, which means that fx is less than fx star. Correct? This is what we proved. But hold on, we assume that this is x star is the local minima. So fx star should be the minimum around any neighborhood, right? Some neighborhood. So this is a contradiction. So basically we assume that x star is minimum, and we assume f, f dash x is not equal to 0, greater than 0, and we proved that x star is not a minima. So that is true. Second case, you'll have to prove it for f dash x less than 0 also. It will have same procedure. And similarly, you can say that for you'll be able to prove it for f dash x less than 0 as well. And there also you'll find some contradiction, and hence you can say that if f dash x star is not equal to 0, then x star is not local minima, which is same as saying if x star is local minima, then f dash x star equal to 0. So hence we have proven the first order sufficient conditions, necessary conditions, sorry, and now we'll move ahead. Now we already know that f dash x is a necessary condition, but it's not sufficient. How can we say that? Let's say we have a function like this, x fx. So here this is minima and f dash x is 0. Okay, so it is minima, then f dash x is 0. But is it f dash x is 0, that's why it's minima? No, it's not correct. We can find many places, like let's say this is true. So here also f dash x is 0. But this is not a minima, this is actually maxima. So f dash x is a necessary condition, not a sufficient. Similarly, we can also find uh, functions like x cube, x fx equal to x cube. Here f dash x is 0. But on one hand side, uh, the value increases, and on the other hand side, the value decreases. So it's not neither minima nor a maxima. Still, the f dash x is 0. So you cannot say that if at some point the first derivative is 0, then it is a minima, local minima. It can be local minima, maxima, or anything. So such points are called saddle points. Saddle points where f dash x is 0 are called saddle points. There is one more terminology used called stationary points. Stationary points. Okay. So we'll just formally define it once. So stationary points. So x star is a stationary point if f dash x equal to 0. F dash x star is equal to 0, where f is a one-dimensional real-valued function and it's continuously differentiable. And this problem we are considering for unconstrained optimization. Okay, then such a point is called stationary point. So that's just a formal way of defining stationary points. And we have already seen that it's not a sufficient condition. So we'll just state it that f dash x equal to 0 is only a necessary condition and not a sufficient one. Okay. Now, but we saw this is not enough. Like only first order sufficient necessary conditions are not enough to find a local minima. So what we'll do, we'll define second order necessary conditions. Please note it is still a necessary condition only. It's not a sufficient one. So we'll first define it and then we'll talk about it and explain it. Let f be a uh, one-dimensional real valued function and let f be a continuously differentiable function, and consider a problem of unconstrained optimization of fx, where you have to find the minima. Then if x star is a local minima of f, then f dash x star equal to 0. We saw it in first order necessary conditions, and f double dash x star is greater than equal to 0. So this also condition similar to this you might have you would have studied in your class 12th, and that is correct, that if at some point you find that f dash x star is 0, and you also find like if some point is a local minima, then you'll find that f dash x is 0 there, and you'll also find f double dash x star will be greater than equal to 0. It will never be negative. So that's what this theorem or condition says. So we'll first prove it why this is so. So again, this is of the similar structure, some statement A and some B. Okay, so we'll not prove this statement, the f dash x star is equal to 0, because this we have already proven in the first order necessary conditions. We'll prove the that's the other condition, double derivative condition. And I made a mistake here because I'm assuming that I'll be able to calculate f double dash. I want second derivative to be continuous also. So this C, it should not be belong to C1, it should belong to C2. Okay, this is there. Uh, Now, so yeah, so by first order and necessary conditions, condition, we have already proven that f test s star is equal to 0, so we'll not do that. I mean, basically it means just following the previous procedure. So similarly, we assume that f double dash x star is negative, and then we'll see that we'll prove it that x star is not a local minima. So that's what we'll do. So let f double dash x star less than 0. This we assume. Hmm. Now we know that f belongs to C2, right? Implies we can say that f double dash is continuous. Basically, it belongs to C0. Now, again, the structure of the proof is similar to how we proved the previous version. We'll assume a neighborhood. Let D be equal to some, say, x star minus delta be some neighborhood plus delta such that f double dash x star is less than 0 for all x belongs to D. So basically this means that this is my x star, some neighborhood around it, delta, this is delta, this is delta, some around some neighborhood, around it, the f double dash x is negative. And how can we assume that it's always negative? Because f dash x is continuous. Same procedure. So because it is continuous, we can always find a uh, neighborhood around the point in which the values do not change abruptly, correct? So that will continuous mean. So we can always find some D, right? So yeah, so we assume this, then we can mark this as 1 because we'll use it later, just like we used previously. Then same as previously, we'll use truncated Taylor series, second order. All right. So so what does this mean? Fx equal to fx star plus f dash x star, x minus x star plus f double dash x bar, x minus x star whole square. So this is what truncated Taylor series second order says, that if you want to find the value of fx which is near to a point fx star, then you can uh, like find it like this. And please note, this is not approximate, this is exact. Okay, so yeah, and now we'll use this to solve that. So let's assume that x belongs to D. So let's say x is in D. We want to see the some value of fx in the neighborhood. Then here fx will be equal to fx star, and we know this is f dash x star is 0. We have already proven it because x star is minima, right? So here 0 plus, we know this is f dash x is negative by 1. In 1 we have proven that we assume that it is negative, and this is always positive, which implies this whole thing is negative, correct? Which means we can say that fx is less than fx star, which is again a contradiction because fx star is the local minima, correct? So uh, so again we have proven it that if f double dash x star is less than 0, then f x star, sorry, x star is not a local minima. Or we can also say if x star is a local minima, then f double dash x star is greater than equal to 0, correct? So this is what we have proven. But again, let us ask us a question. Uh, are these second order are these second order conditions, second order necessary conditions sufficient? Can we say that if we find something like this, will it be sufficient? So actually the answer is no, they are not. So they are not because you can find a local minima uh, in which you can find a point where f dash x and f double dash x are both uh, 0 and greater than equal to 0 are 0 and greater than equal to 0 respectively, and still it is not a local minima. um, that can happen. So for example, one example is x cube, fx is equal to x cube. So for this, f dash x is uh, is 2x square, and f double dash x is sorry, 3x square, and f double dash x is 6x, correct? So f dash 0 is 0, f double dash 0 is also 0. So uh, I mean, this is not like this is a saddle points. So actually this is true, right? So f dash x star is 0 and f double dash x star is greater than equal to 0. So uh, this actually suffices the sufficient second order condition, necessary second order condition, but actually it's not a minima, it's a saddle point, as we all know, right? So it's something like this. So these condition are so yeah. So if some of you are wondering, oh, it's 0, right? So we can say something. But the thing is, the condition is equal to. So we can't say anything about this as of now. So for those you are saying, oh, if it is 0, then it is not. So you are correct. That is what we want to define the next condition, which are called as sufficient conditions. So second order sufficient condition. So again, I'll just state it once and then I'll discuss about it. So let f be some single dimensional domain and real valued function. F belongs to C2, where second derivative is continuous also, and consider a problem in which we are try to optimize fx, find its minima, uh, and there are no constraints. X belongs to R. Then the second order sufficiency condition says that if f dash x star equal to 0 and f double dash x star equal to is greater than 0, then x star is a strict local minima of f. You can say over R. Over all of the real numbers. So this is what necessary condition says, that if f dash x star is and f double dash x star is greater than 0 and f dash x star is 0, then it is a local minima. That's what it says. This is called sufficiency condition. So like always, we'll again prove this. So, uh, so, so again, so this time what we'll do is will not, so it's again like this, right? If this is true, then that is a local minima, right? So this time what we'll do is, this sum called A implies B, right? We'll assume A and we'll prove B. This time we'll do straight, not contradiction. This is not going to do that. The structure is the structure of proof like that. You can always do the reverse, but it kind of if you can try it yourself, but you'll find that it is difficult to assume not of B. So and then prove the not of A. That will be difficult in this case uh, because if you know these conditions have flipped from the previous conditions, so that will do. So we'll assume the first things we have been given that f dash x star equal to 0 and f double dash x star to 0. We'll assume this directly. We have also been given that f belongs to C2, which means f double dash x belongs to continuous. So basically it's a continuous set. F double dash is continuous. That's what we know. By this condition, we can say that if f double dash is continuous, we can assume a neighborhood. Let D be a neighborhood around x star plus delta neighborhood such that f double dash x greater than 0 for all x belongs to D. So basically, we are again trying to find a neighborhood around x star such that the double derivative is greater. And how can we assume such a neighborhood? How do we know that it exists? Because f double dash is continuous. So that's how we assumed it. Now we'll again use the second order truncated Taylor series, and I'll just write it first. Fx to fx star plus f dash x star x minus x star plus half times f double dash x bar x minus x star square, where x bar belongs to between x star and x. If x is smaller than x and x star. So this is the truncated second order series, uh, and we have assumed that f dash x star is 0. So this term goes to 0, correct? So what we can write is fx is equal to fx star plus half times f double dash x bar x minus x star square. Now we know that we already assumed that if let's say x belongs to t, so let's say this x belongs to d. So x we have kept in that neighborhood d where f double dash x is positive. Then we can also say x bar also belongs to d, right? Because x bar is between x and x star. So I think this is confusing. So this we can say, right? These two things. And we assume this, correct? So we can say that this is always uh, positive, correct? This is always positive, and this is positive always, right? Correct? Implies we can say that fx minus fx star is equal to half f double dash x bar x minus x star square. Uh, this is greater than 0 for all x belonging to D. Can we say that? I think, yeah. So based on previous analysis, we can say that, right? This is greater than 0. We can write this as fx minus fx star is greater than 0 for all x belonging to neighborhood of x star, some neighborhood of x star, which means For all x, fx star, there exists some neighborhood D such that fx star is minimum. So basically x star is a local minimum. This helps us say that x star is local minimum. Correct? So we proved that. Um, so that is that. If anybody has any questions regarding this proof, they can ask. But I think most more or less you can go back and study these proofs yourself to understand it and can ask question later. But the main idea you should remember, which I think you remember from your class 11th and 12th, these conditions, these are really important because these conditions will build up on them in multidimensional optimization. Okay. Now we'll again ourselves a question. Uh, are these sufficient conditions? Second order. Are these necessary? The sufficient means like if these conditions are true, then I guarantee that this is a local minima. But do all local minima have these conditions true? It's like that. Is it necessary? So the answer, unfortunately, is no. They are not necessary. So for that, I want to give you an example. So let's say fx is equal to x to the power 4, correct? Um, f dash x is 4x cubed, f double dash x is 12x square, correct? So now f dash 0 is 0, f double dash x is equal to 0, correct? But it is known that x is equal to 0 is a local minima for x to the power 4. Okay, this is a known fact. Like if you would plot it, it will be something like this. At 0 its value is 0 and it's a local minima, but these conditions are not true. So basically we can say that if we can find a point where f dash x star 0 and f double dash x star is 0 is greater than 0, then we can say that that point is definitely a local minima. But if there is a local minima, are these conditions true? Not necessarily. So this is not a necessary condition. So so with that, we'll move ahead and we'll define the final conditions, which will try to solve all your answers to all your questions, give all the answers to all your questions, which is called sufficient optimality conditions. Conditions. So again, I'll try to first state it and then I'll try to explain it. So basically, let's assume there is a one-dimensional real valued function, and this time f belongs to C infinity, which means that all its derivatives are continuous, or it very high order derivatives are all continuous. Let's say f is like that. We'll also assume let f is not a constant function. We are ignoring this because for a constant function, every point is a local minima. So we actually don't need to analyze this. So we can ignore this case. And so you'll see that uh, it has some problems which I'll come to later. But you can see that if there is a constant function, then every point is a local minimum. And let's say kth derivative be represented by f k x. So instead of k primes, I just write k there. So that is like for the representational purposes, I use this as a kth derivative. Now we again have the same problem. X belongs to unconstrained problem minimization of fx. Then the first theorem or first condition is, or this is a local minimum if and only if. So it's both necessary and sufficient. So this is if and only if. This is both necessary and sufficient. The first non-zero element of sequence fkx. So basically it is saying the first non-zero element of sequence fkx. So let's say you make a sequence f dash x, f double dash x, f triple dash x, and so on. A sequence of kth derivatives of the function. Then the first non-zero derivative, basically this is what this statement is saying, is positive and occurs at an even position. So let's say first derivative is indexed 1 and subsequent 2, 3, 4, 5, etc. Then the first non-zero derivative should be positive and should come at even position. Then we can say that that point is a local minima, and it is an if and only if condition, so it is necessary and sufficient. We can write a similar statement for maximization as well. So I'll just go ahead and write it. So same thing, but for maximum. So x star is a local maximum if and only if the first non-zero element of sequence fkx is negative and occurs at an even point. Again, even position for maxima as well. It's just that the sign changes. So then it is called a local maxima. It is a local maxima. It's a necessary and sufficient condition. Thing is, what happens if the non-zero element is on odd positions? So it turns out that those kinds of points are saddle points. So it's neither local minima nor local maxima. It will be that x cube zeroth point of like zero of the x cube. It will be like something like this. Okay. Uh, okay. So these are some necessary and sufficient conditions. The thing is, I will not prove these theorems or prove these conditions, but you can. These are the most important conditions for you to remember in this lecture. Uh, 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 that's that. Now we'll do some examples. So just to like how to use these theorems or conditions. So let's say we'll start with a simple example. X belongs to R, x minus 2, x square minus 1 whole square. So we have to minimize this. So first we'll take the first derivative. So it will be 2x square minus 1, 2x, which can be written at 4x, x square minus 1. Okay. And we can also take out f double. So we calculate calculate the stationary point first. Let's say let's see whether there is a zero that exists or not. If there is no zero on f dash x, then it's a monotonic function, so we cannot find a minima exactly. So 4x x square minus 1 equal to 0. Then we have three zeros, x equal to 0, 1 and minus 1. Okay, so we'll check f double dash x in these 3 points. So f double dash x equal to 4x square minus 1 plus 4x 2x equal to 4x square minus 4 plus 8x square 12x square minus 4. This is double derivative. If we put, so f double dash 0 equal to minus 4. Okay, f double dash 1 equal to 8 and f double dash minus 1 is also equal to 8. So we had to minimize this, so these two are local minima. How can we say that? So this is by uh, sufficient conditions for local minima. Okay, second order sufficient condition, this is true. Okay, we can also use the sufficient optimality conditions as that. So first derivative is 0, second derivative at this point is 8, so hence uh, uh, this is an even position. Please note, for using the final these conditions, final conditions like this, you will have to know where the stationary points are. Otherwise, you'll have to find it at every point. So it's good to find where the first derivative goes to 0. So yeah, that's why we start with f dash x is equal to 0 always. So it's at the even position, and hence it is a local, and it is positive, so it's local minima. On the other hand, this will be maxima, but because the problem is minimization, so we don't care about this. But this will be maximum. You can plot the function and also see. Let's see a second question, which is a little bit interesting one. Second example. So it's like minimization of x unconstrained x square minus 1 cube. Now let's f, what is f dash x is 3 x square minus 1 square, so 2x equal to 6x x square minus 1 whole square. Okay, so where is it 0? So stationary point, let's find stationary point. 6x x square minus 1 whole square equal to 0 implies x equal to 0, or x square minus 1 whole square equal to 0 implies x square is equal to 1, x is equal to plus minus 1. So x stationary point is 0, 1 and minus 1. Correct. Now we'll look at f double dash x. F double dash x will give you 6x square minus 1 whole square plus. So I'm doing it faster because I know that you will understand this differentiation and double differentiation. You can try all of these at home once to get hold of it. Or maybe you can pause once I write the question, do it yourself, and then continue the video if you are watching it on YouTube. So this and 6s to x square minus 1 dot 2x. Okay, so this is the double differentiation. We'll make x square minus 1 common, 6x square minus 6 plus 24x square. I think this is what it is. If I'm wrong, please correct me. 330 x square minus 6, so x square minus 1. This will be 6 times 5x square minus 1 x square minus 1. This is a double differentiation of x. Now we'll try to see what its value is at 0, at 1 and minus 1. So f double dash x 0 is 6. F double dash 1 is 6 into 5 minus 1 into 0, so 0. And f double dash minus 1 is again 0, right? So we can't say anything about this, but this is definitely a local minimum. Correct. For others, we'll have to do further differentiation. So f triple dash x, what does that come out to be? So 6 10x x square minus 1 plus 6 2x. To 6 I'll take common, 12 I'll take common, and here it will be 5 x square minus 1 plus 5x square minus 1. So 5x square minus 5 plus 5x square plus 1 with 10x square minus 6, 12x 0. So f triple dash x at 1, what will be its value? It will be 12, 10 minus 6 equal to 4, and f triple dash minus 1 minus 4, right? So you turn out that at the odd position, this is non-zero. So basically these are saddle points, which means that 0 x is equal to 0 is local minimum. Correct. Now there is a third example, which is a very simple example, which we'll look at, which we already saw, I think, but just to give you a better understanding of that question. So fx is equal to, right, fp from r to r, x fx is equal to x square, x to the power 4, and the problem is minimization of unconstrained minimization of fx. Okay, so again we'll try to find fx equal to 0, implies that 4x cube equal to 0 implies x equal to 0. Correct. Now f double dash x, so stationary point is x equal to 0. F double dash x will be 12x square, f which is also 0 at 0. So actually we do not get any information. F triple dash x is equal to 24x, which is also 0, and fourth derivative is 24, which means 0 is 24, so which is positive and is on the even position, so this will be minima. Correct. We found our minimum. So this is how you do the the optimization of single value variable. These are the some optimality conditions. Now you will ask, why, if it is so simple, why do we need algorithms anyway? So why do we need algorithms? Why are we studying even this? If it has analytical solution and it's so simple. So the thing is, as I told you earlier, to solve these kinds of problems, necessity of an algo. Why are the algorithms necessary? So for solving any of these equations, you have to solve this equation. You have to find those stationary points always. And sometimes solving these equations are not trivial. So you cannot find the solution analytically. You'll have to use the numerical methods, and that's where these algorithms come in place. So for example, consider an example fx equal to x square plus e to the power x. For it, f dash x, let's say we call it gx, is 2x plus e to the power x. And we have to, for finding the stationary points, we'll have to find solution to the equation gx equal to 0, which is 2x plus e to the power x equal to 0. Now, solution to this equation, we can't find it through hand or analytical solutions. We need a numerical solutions, and we need the help of computers. So that's why we require numerical techniques. So which we'll study in our next lecture, which are some numerical algorithms to solve one-dimensional optimization problems. That we'll study in the next lecture. So yeah, so to summarize everything, today we studied what are first order necessary conditions for optimality. We also studied second order necessary conditions for optimality, and we also studied second order sufficient conditions for optimality. And we realized that these two are not sufficient, and this alone is not necessary. To state them here is first order or first, or wait, I'll just I'll just state it once for the revision, for the sake of revision. The first order necessary condition is the local minima implies f dash x star equals 0. This is what it means. But this is not sufficient. If f dash x star is 0, that doesn't mean it is a local minima. It can be a saddle point also, or a maxima, let's say. We also studied that so we also studied that if local minima, then f dash x star is 0 anyways, but f double dash x star is greater than 0, greater than equal to 0. We realized that this is also not sufficient. So we went ahead and studied second order sufficiency condition, which means if fx star equal to 0 and f double dash x star is greater than 0, then local minima. That point is x star is local minima. But we realize this is not necessary. Not all local minimas have fx star and f dash x star and double dash x star is 0. Then we talked about the necessary and sufficient conditions for higher order. So we said that uh, sufficient and necessary condition. So we said that we'll go on the uh, derivating the objective function, and the first non-zero, element of this sequence should be a positive, and if it is on the even side, then that point is a local x star is a local minima. So if this kth is even and it is positive, then x star is minima, and this is both sufficient and necessary condition. And if it occurs on odd position, then it is a saddle point, not a local minima. So with that, I'll end the lecture, and we'll see in the next lecture. We'll talk about algorithms. Thank you.